Hello, welcome to the tag kickoff, the assembly group. So, if you're wondering about this is me recording a video of the meeting because we actually did not do a live recording. Um, so, here is about us. So, I'm the president, I'm Henry Wang, and the vice president is Xander Wong, secretary is Sean Kennedy, and the treasurer is Rashali Assar. And then here is our website at the bottom. Feel free to pause the video at this place to get our contact information. So what are we? So we are the assembly group, and we are abbreviated as TAG. So in this assembly group, we will actually address a few different topics, a few questions that you might have about assembly. And in this short meeting, we'll actually also address these same questions, but more briefly. So first of all, you ask maybe who is this for? What is assembly? So if you haven't taken like any classes like computer architecture, you probably have very limited idea of what assembly is. So why should we learn assembly? Sometimes assembly might be a little bit on the boring, but there are some interesting and key aspects about assembly that make it stick out. Furthermore, sometimes learning assembly is critical. What will we do in TAG? So I will briefly discuss later on. And then how do you use assembly? Later on, I will actually do a demo of how you would use an IDE in Windows. So who is this for? This is for everyone. We welcome everyone to join, no matter how, whether if you have any experience or not in assembly. We want this to be a fun learning environment for assembly. What is assembly? So, unlike a lot of different languages like C or Java or C++ or JavaScript or any other languages you probably have been accustomed to, assembly is actually a machine-friendly language. Many of the other languages you have been accustomed to are human-friendly languages. So typically, you would have some sort of compiler that converts your human-friendly languages, also known as high-level languages, into assembly. And then this is the assembly that actually gets run directly on your machine. So we will focus on x86 assembly, because it's actually used by most PCs and also by modern day Macs. So then, unlike anything you have done with high level languages, when you write an assembly, you are able to write commands directly communicating to your computer. On the other hand, when you write in high level languages, you're only writing suggestions that the compiler actually goes and writes the real code. So why would we want to learn assembly? It's interesting and fun to learn. Sometimes there are some vulnerabilities that you could not understand at the high level, but you would be able to fully understand at the assembler level. And later on, I will actually show you such a vulnerability. And then in assembly, we can optimize more freely. Unlike high-level languages, in assembly, whatever code you write is what it will be present. No more, no less. Pretty much. So, in TAG, we will start off with some interactive assembly workshops. What are they? So basically, we will do basic tutorials on assembly, and then we will give you fun projects to work on to exercise those. So then we have also some interesting tricks and techniques that we can do in assembly that aren't really that possible in high-level languages. And then we can also describe vulnerabilities at the assembler level more detailedly than what we would have done if we were just working with high-level languages. And then now I will show you how to install NASM or SASM on Windows. So this is how you install SASM. So first of all, open up your browser. And then type in SASM. The link is also in our instructions. So what we want to do is click on this link to download for Windows. I already downloaded it, so it's actually over here. This is the thing you'll get. So you'll just double click on that, and then you will run through the wizard. I accept, next, create that. So then once it's installed, it'll ask you to open it, and then here we have SASM. So then let's first create a new project. But first we have to install something else. We have to install a NASMX. So go to this download. When you download it, you'll click on this. You'll get a zip file, which is right here. This one, which I already unzipped it. And you will get all these files. So we are actually interested in the ink folder. So we have all these folder files here. So let's copy these. And then we now have to navigate to where we installed SASM. So so if you installed in the default location, it'll be under Program Files, x86, SASM. So now we are in the SASM where we installed SASM. Now we have to go into Include folder. So in the Include folder, we have two files. So what we want to do is copy it to this location. And if it asks you for permission access, just click Continue. So now you have, these are the files that from NASMX that help us be able to program in assembly much more easily. So now we have that. So now let's go into our GIST, which is right here. So this one is our little program, Hello World program that we're going to run. I also have a tiny URL right here in case if you need that. So now I have this. So I just copy the entire thing and paste it all into SASM. So if I run it, if I build it, it should build successfully. If it doesn't build successfully, chances are you haven't installed NASMX. This requires NASMX to work, and that was in my instructions that we just did. If something else happens, please do let us know. And then, so now we have a very simple program that prints Hello World. So I'll briefly run down what each of these statements mean. So we have these first statements. These are just comments. So notice how you put a semicolon, which denotes the beginning of a comment. You can also put it right here. Comment. Next, we have this include statement. We have a specials percent, which tells us this is a directive. So this one says to include from this NASMX file. So this is our file that helps us actually make some interesting stuff, define some interesting stuff for us. So now we go to the next statement. This import allows us to import this printf function. So normally when we just compile assembly, we actually do not have access to any of these functions. Functions like printf, puts, or any function you can think of are actually part of the standard C library. And typically, if you have just bare assembly, you don't have those. So next line, we actually define that our entry point is in the main proc, which is this one right here. So after that, we have something called a section. We have two section statements. One is a data section, one is a text section. So the data section does what you think it might do. It contains all the data. So like strings, variables, and of that sort. So now we have a something like a label. So a message. This one defines like a variable. And here we see that we define a variable to contain the string hello world, and then you have a byte with hex A. This is a new line byte. because in assembly we actually cannot do escape key like this. This actually does not work in assembly or in NASM in particular. So now we go to text section. You might think that this contains text like strings, but actually the .text means actually code. So this actually means code. So this is where all your assembly code goes. So we start with a procedure definition. So we define a procedure named mainproc. And then we have locals, none. This is saying that we do not have any local variables defined in our function. And then we have an invoke. The invoke is the way that you can call functions in assembly. Particularly, this is actually defined in NASM-X. So this allows you to call a function printf, and then you pass one parameter called message. So then here we end the procedure and then return from this method. Very simple. And then if we run it, we see that this is output right here, hello world, and we printf hello world right here. So that is our simple SASM. So now let's move on to something else. So here I have a program in C. You might ask, this is assembly. Why are we working with C? Well, you see, when we compile code, there's some stuff that is compiler dependent, meaning that, like in C, sometimes we have a bug, and it's not very evident what will happen when you just look at the C code. But if you know the underlying assembly, you actually have a better picture. So here I have some C code, and it has a bug. Feel free to pause this video to see if you can find the bug. Okay, so here I have a main function right here, and this calls a function called greetings. This greetings function is right here. It declares a local variable named buff. And then we say, hello, what is your name? And then we call a gets, which is a way to get user input. And then we spit back the name. We pass in the parameter buff, which is the one that we had read in the name from user input. And then we say, cool, something, something. Welcome to the assembly group. And then once we finish this method, we return. We go out here to this puts statement and says that's a wrap, folks. So here, let me run the same program to confirm that. Oh. Hello, what is your name? My name is Henry Wang. Cool. Welcome to the assembly group. And that's a wrap. So, nothing useful. Or so you think. So the interesting thing is, here we have something like a gets method. But how does gets know that our buff is only 32 bytes in length? It actually doesn't. So you can actually type in a longer string than 32 bytes. What happens? See? What we end up is we have a segmentation fault. A segmentation fault. But didn't we just overwrite, like, we just passed the buffer? Shouldn't it be like an index out of bounds? Well, not really. So a segmentation fault means that we access a part of memory that we shouldn't have. But we just only wrote a little bit more than the end of the buffer. Why is it that we're accessing some memory that we aren't supposed to? Shouldn't it be like maybe there's like a lot of memory? Well, yeah, but there is a problem because the variable buff is actually not the only thing that's nearby. So we now introduce something called a stack. Briefly saying is a stack helps us keep track of the function calls we had. So for example, we call greetings. The stack tells us that we just called greetings, and then after we finish calling greetings, we return to this statement right here. the put statement. So in order to be able to figure out where to return to, at the assembly level, we actually have placed a return address onto the stack as well. So this very local variable called buff is actually also on the stack. So what happens is when we write to this buff variable, we actually overwrite our return address as well. So that's what happened here. We overwrote our return address, and we get a segmentation fault when we try to return to a part of memory that we aren't supposed to. Turns out we can actually control where we go to using this method. So I actually never told you this secret method, but this method doesn't actually get called. So what's the point? So here we actually have an interesting function call to system, and then we call this command bin sh. That helps us get shell. Wait a minute. Is there a possibility we can get shell from this program? Let's wait. Let's see. So normally, since this is not actually called, you shouldn't be able to access shell, and hence that is probably not the original programmer's intention of giving you shell. But here I have an exploit. Let me pull it up. This interesting command which pipes it into the simple program. We do an echo, and then we echo this return address, and then we echo it right into simple. So if I run this command, we actually get something interesting. We say, hello, what is your name? Cool. And then this name. And then we have some junk over here. But then we get, wait, how did you do this? It's this statement right here. So now, the next statement, we actually got shell. So if I type in ls, we get a list of files. And if I do echo, we get an echo. So it turns out we actually got shell. See, this stuff like this might seem magical to you, but everything that you see here is actually hidden inside the assembly level. So theoretically, we can actually read the assembly code and actually figure out why this bug works, why this exploit actually gives you shell. So today, I don't think I will be able to really go in depth into explaining this exploit, but I hope that in future sessions I will actually be able to take a step further and actually explain why this works. And we hope to see you in our next meeting of the assembly group. Maybe I will go in more depth of this, why this works, and then maybe how to read assembly to understand the underlying principles. Thanks for watching. We hope to see you again.